Hello, everyone. We're working through statistical methods for rates and proportions, chapter 12, section 2. All right, we are looking at Poisson regression, and we're going to start with simple Poisson regression. And we are in the situation where Y is a Poisson count associated with given units of observation, right? So Y could be the number of cancer patients in a region over a period of time, the number of defective products in a factory, the number of pixels in a positron emission tomography scan, or a cell count in a contingency table. Okay, we are going to recreate the table 12.1 for smoking and lung cancer. So we have cigarettes per day, person years, number of cases, the observed rate, and the fitted rate. Okay, so to start this, we're going to create 12.1. And we get most of table 12.1, except for the very last part, the fitted rate, because I didn't want to hand put in the fitted rate. I want to use those values to actually calculate it. Okay, so we are going to fit a model similar to 12.14. in the textbook using the function GLM. And what we do to do this is we say that Y follows X. So the number of cases, because that's the count, is following the average number of cigarettes per day that a person consumed. The family is Poisson because the Y is a count in an observed amount of time. Okay, the offset is going to be the log person years. And we use summary fit to calculate our estimates. So here we get the estimate for beta 0 to be -7.14. And the estimate for cigarettes is 0.07. All right. So what I want to do here is to tell you and to note that the weights of a Poisson model are equal to the fitted values. So I'm going to just plot them and see if they lie on a line. And they do. So we see that in general for a Poisson regression, these weights are going to be equal to the fitted values. Okay, so our sum of WI, which we need for the equation 12.15 to eventually get the standard error hat of beta 0 hat, right? To get this estimated standard error, we're going to need the sum of WI, right? We're going to need X bar W, right? And X bar W is defined on the bottom of page 347 as the sum of the WI times XI divided by the sum of the WI. Okay, so we define X bar W. We get 26.58. All right, we're going to calculate SSW, which is on the top of page 348 before equation 12.15. And we get SSW as 4088.53. Okay. From there, we're going to get the standard error. I used alpha hat here and beta hat, but in the textbook, they use beta 0 hat and beta 1 hat. It's all the same. So we get equation 12.15 by getting the estimated standard error. Is 0.4540. But if you notice, if we would have gotten the summary of the fit 1 $ coefficients, right? 1, 2. So what I'm saying here is if I look at the coefficients all together, summary of fit 1 $ coefficients, I'm saying give me the first row, second piece. So I'm saying give me the standard error. That's the same value as the equation we just plugged in using 12.15, okay? And the standard error associated with cigarettes, the coefficient for cigarettes is 0.0156. Using equation 12.16, that's 1 over the square root of SSW. So we can get the standard error beta hat. But similarly, we could have said summary of fit $1 coefficients, give the two element second row, second column, and we still get 0.0156. All right. If we want, we could use the covariance formula, right? That's negative x bar w over SSW. That's equation 12.17 in the text. We get negative 0.0065. Okay. If we wanted to, we could look at the summary of fit.glm $covariance unscaled. And if you notice, it's in the off diagonal. So we could have picked off the 2, 1 element or the 1, 2 element. Either one would have given us the same exact thing. But it doesn't really matter. You can either hard code these equations 12.15, 12.16, and 12.17 into R, or you can use the custom built-in functions, which someone else had to hard code the equations for. Okay, so here we get the standard error for alpha hat, beta hat, the covariance of alpha hat and beta hat, and x0, which are the cigarettes. Okay, so let's just take a view of the values. We've already seen them, but there they all are, all in a row. And if we want to get the fitted rate, we can take the fitted values and divide that by person years, right? And then if you look at the standard error of the fitted values, right? This is shown under equation 12.17. It doesn't have an equation number on it, but it says the standard error of the predicted value of the expected value of y given x can be derived using the delta method. And here's the equation. This says get the fitted values and multiply by the standard error of beta 0 hat plus beta 1 hat times x. So if you go back to the logistic regression section, we had this equation already mapped out from a previous section. That's the standard error of alpha hat squared plus 2 times x0 times the covariance plus x0 squared times the standard error of beta hat squared. So here we now have 12.1 plus a little more information. So we get the fitted rates that we saw in 12.1, right? We also have calculated the fitted values for each of those observed cigarettes values. And we calculated the corresponding standard errors for each of those expected value of the number of cases given the cigarettes, right? So essentially here, we'd say that for people who have not smoked, right, we would expect 1.13 cases. And the standard error of that expectation given 0 cigarettes would be 0.5118. Okay. So we can exponentiate those coefficients, right? And if we wanted to, this is giving us the those estimated values of our coefficients, right? Because originally we modeled based on the log, and so we're exponentiating these to get the values that we're interested in. We can get the confidence interval for our fit, right? So here we get our confidence interval for beta 0 hat, or excuse me, for beta 0. And it's based on beta 0 hat. And we get our confidence interval for beta 1. And what we can do there is we can exponentiate that confidence interval to get it back on the scale of the rates. And by doing that, we see that our confidence interval for the effect of cigarettes, right, is a slope of 1.05 to 1.11. All right, make sure that you can get all these values, and you can check that last paragraph of 12.2.1, and you'll see that all the numbers are matching up well. And that is the start of modeling for Poisson regression. I'll see you next time.